Okay. So I only have 25 slides today, so if you don't ask questions, it's going to be a very early break. So I would very much encourage you to interrupt me whenever you have a question or comment. Okay. So today I'm just going to talk about primarily sparse matrix representations and also give you a little bit of an idea of how this fits into iterative solvers and what that really means. So when we say sparse matrix, what do we mean? So people are probably, if you've ever had a class in linear algebra, familiar with a dense matrix. And here I have a 6 by 6 matrix. And the boxes that I've illustrated in each of these cases represent the non-zero entries. So on the right-hand side, we only have 3 non-zero entries in the first row, 2 non-zeros in the second row. And they sort of have this kind of pattern. You'll notice that it happens to be symmetric in this case. So above the diagonal looks the same as below the diagonal. That's actually a pretty common thing. So there's really no hard or fast rules for what makes a sparse matrix or when a matrix becomes sparse. So a sort of practical definition is a matrix is sparse if there's some value in exploiting the fact that we have lots of zeros in the matrix and we want to store it more efficiently or consider different numerical methods that exploit this kind of structure. So a sparse matrix could be like this, where we have 3 or 4 non-zeros per row. Could be that only 3/4 of the entries are 0 or something like that. Just depends on the problem and the application area. So sparse matrices arise in a lot of different places. Probably the most interesting application area for this audience is things arising due to mesh discretization. So we have a PDE and we want to solve it, and the way we solve that is by splitting up the space into simple elements. So perhaps squares in 2D or triangles for an unstructured mesh. And these are sort of standard ways of breaking up our space into simpler elements. And then the idea is that on these smaller elements, it's much easier just to describe the physics or the interactions between different components. Structured meshes, so here I have just a bunch of squares. You could imagine cubes or other things that just have a regular tiling pattern. The nice thing about them is that they give rise to sparse matrices with a very well-defined pattern, and we can exploit that. Unstructured meshes like this are a little bit harder. We need a more general kind of representation for these. They're a little harder to work with. But still, even within unstructured matrices, there are different kinds. There are some that are really weird. Like this is actually, even though it's unstructured and you can't say exactly how the pattern, the sparsity pattern will look like, you can still say certain things about it. For instance, the average number of neighbors of a vertex in this mesh is about 6. So there's, even within unstructured meshes, there's, more or less regularity to be had. Finally, these are the physical sorts of problems that we can represent with sparse matrices. This very same technology that we'll talk about here can also be applied to, problems in graphs. So, perhaps the graph represents, hyperlinks. So the PageRank algorithm that, was Google's innovation is based on sort of taking hyperlinks in the web, representing those as a matrix, and then solving an eigenvalue problem. Social networks. So a lot of people are very interested in just looking at graph problems and solving them as efficiently as possible, finding clusters in a graph. Maybe they want to look at your social network and find out, do you like this? Oh, your friends like this. Maybe I'll recommend that to you as well. And of course, the government's very interested in this sort of thing as well. Okay, so when we say sparse solvers, we mean we have a sparse matrix. So anything that you can think of as I described before, we want to solve AX equals B, where A just happens to be sparse. So we want to solve, we have a column vector X and a column vector B, and we want to solve this somehow. So if you're familiar with, the standard way of doing this for dense systems, you probably were introduced to row reduction or Gaussian elimination. Or maybe like LU factorization. That is one class of techniques that are applicable to dense matrices, but not so applicable to sparse matrices. Just because if we were to apply that kind of procedure here, most of it would be wasted. We don't really care to play with the zero entries in this matrix. We just want to work with the non-zero entries. So really that sort of gives rise to two classes of solvers. There are direct methods, which are sort of sparse analogs of LU factorization. And then there are iterative methods, which is what we'll talk about in this series. But just to give you some idea of what the distinction is, because it's not always clear what these names mean, I'll give you a couple slides on direct methods. So direct methods, I guess the way to understand it is when you have an LU factorization or something, you have a finite procedure, which at the end of the day, if you had exact arithmetic, you have the answer. Of course, because we're doing floating point arithmetic, that's not entirely true that we have the right answer at the end of the day. But still, you have a pretty, regular algorithm that's going to produce a solution for you. It's going to produce an X that solves AX equals B. So direct solvers in the case of sparse matrices are sort of the application of these ideas to a sparse system in an optimized way. And the way it works, and there are a variety of codes that do this, is they take a matrix. On the left-hand side, we have a matrix. It's, I guess, maybe 25 by 25. It has 105 non-zeros. And what they want to do is produce an LU factorization, but they want to produce one such that L and U are as sparse as possible. And the way they do that is by reordering the matrix such that when they do this optimized LU, they don't introduce more non-zeros than necessary. So what I've illustrated here is the original matrix, a matrix where somebody has cleverly reordered the rows and columns of the matrix such that when we go and compute an L and a U, they have as few non-zeros as possible. So it's not really possible to do this optimally. I'm not claiming that that's what they're doing, but it's sort of a set of heuristics, and there are lots of different ways of reordering matrices, but there are a set of heuristics such that we believe the L and U will be as sparse as possible. So the different codes here, Paradiso, UmpPack, SuperLU, there's active research in these areas, and they have improved quite a bit. And these are sort of the standard technology. Like if you use MATLAB and you say, solve this sparse linear system, MATLAB \\. If it's a sparse matrix, you're going to get UmpPack, or perhaps if it's a specialized matrix, you're going to get a specialization of that for Cholesky factorization. But ultimately, this is a very robust, rigorous technology. It can fail. You can run out of memory. You can say, this matrix has terrible condition, I can't solve it. But at the end of the day, it's a nice thing. It's sort of a black box. You just give it your matrix. If it can produce a solution, you can sort of trust it, or at least know how untrustworthy it is. The problems, we'll discuss a few problems with this class of solvers, but for the most part, this is very nice. And if this solves your problem, don't care about anything else I'm going to tell you. Just use these things. Iterative solvers, in contrast, so direct solvers, you had a finite sort of procedure. You got an exact solution if you had exact arithmetic. Iterative solver is different in that we're going to apply a procedure such that we steadily improve our solution. So we start with anything. Could just be an arbitrary vector, could be a zero vector, doesn't matter. And we're going to steadily improve that until we converge to something very close to the true solution. The way we measure that, so we want to solve AX equals B. The way you can measure how close you are to the solution is through the residual. So it's the difference. So we'd say B minus AX is equal to the residual. And the reason for this name residual is that if you have an exact solution, then B minus AX is 0. So if you have an approximate solution, so something not the true solution yet, this residual is going to be some non-zero vector. And the size of this vector, and you can measure it in different ways, but the size of this vector is sort of how far away from the true solution we are. So if this residual is large, so if we look at the magnitude, take the Euclidean norm of this vector, and it's large, then we're going to say we're not very close to the solution. If it's very small, say to the point of floating point accuracy, then we're going to say maybe we're as close as we can hope to get. We're close as the physics dictate. Let's just stop going.
Yeah, be a little careful there. But you can add any scale to it. 0 is 0.
That's right.
Like you can scale by epsilon, and it looks small.
That's right. So the point made is that you can't just naively look at this, and it's true because you can scale both the left and right hand side. So usually what people do is they say, the tolerance is relative to the magnitude of B, or perhaps the magnitude of AB or something like that. One thing to know about the residual is, it's really our best estimate for the error. There are different sort of perturbations of this idea, but if you look at B minus AX, we define this as the residual. Another way of thinking of the residual is that if we know the true solution, A prime here, then the residual is equal to A times the error. So if we look at the difference between the true solution and our approximate solution, so A prime is our true solution, AX is, what's that?
You mean X prime.
Sorry, yes, X prime. Then that's the same as A times the error. So the residual is sort of the error that we have left in our solution times A. So it's the transformed error, but it's our best thing that we can look at because we don't know the true solution yet. There are a lot of different iterative methods. Some of the more common ones that you may be already familiar with are listed here: Jacobi, Gauss-Seidel, conjugate gradient we heard about last week. GMRes is another common one. We'll talk about these later in the week. I just wanted to throw out the names in case you had heard them before. So to give you a summary of the sort of advantages and disadvantages of direct and iterative methods, direct solvers, as I mentioned, are very robust. They're black boxes, so MATLAB / usually just works. You don't have to be very sophisticated, just use it. One problem with direct solvers is that they're difficult to parallelize. Most people, when they talk about parallelizing these, from what I've seen, they talk about just doing maybe 20 nodes or something like that. You really don't get much speed up. They usually do this just to have enough memory to store the factors that they're going to produce. So there's very limited ability to parallelize these. I can't give you a negative result that says it's impossible. It's just that people have scaled these up to tens of thousands of processors, those maybe to 10, and not even getting good speed up. Another issue with direct solvers is the memory consumption. As the problem size grows, the size of the factors grows superlinearly in most cases. And you can actually prove this even with optimal orderings for certain problems, that the memory consumption, if you go to from 100,000, which is typical size to solve with these, to maybe 1 million, you might exhaust the memory that you have in your workstation. So if you want to solve problems with billions of unknowns, you're almost certainly going to be in this iterative solver class. As I said, limited scalability also. If you're going to distributed things and you're doing direct solvers, you're mostly doing that just to have enough memory. In contrast, iterative solvers, they're not as robust. Some of these are very fragile. You have to be pretty sophisticated just to understand what's going wrong. So if you want to just apply iterative methods, you have to have a little bit of awareness of what the technology is doing just to understand how to tweak the knobs and use them. They have a lot of parameters. So I showed before, when do we stop the iterative solver? We have to say what the tolerance is. In other cases, there are a lot more parameters, things that control the internal mechanisms of the method. We'll talk about that later, but the point is that in order to make effective use of these, you have to be aware of a lot more than you did in the case of direct solvers. On the positive side, iterative solvers are much easier to parallelize. They can scale up to tens of thousands of nodes. Much lower memory footprint, so in lots of these cases you can actually say up front what the memory consumption is going to be, and it's usually very modest. And lastly, they're very scalable. So not only can you make use of lots of processors, but you can actually get good speed up with increasing parallelism. So we'll look here at probably the simplest. I don't know how you could construct a simpler iterative method. And this one's called Richardson iteration. It really doesn't even deserve a name. And the way this works, so we're at each step, and we're going to apply this inner loop many times. In this case, we applied it 400 times to get to a reasonable solution. We compute a residual, so we're computing R. We're going to look and see if R is greater than the tolerance. So in this case, we cut it off at 10 to the minus 5. And that's about single precision accuracy. So if you're doing things in single precision, maybe this is good enough. And we're going to continue iterating this process. So at each step of the algorithm, we're going to take X, so our current approximate solution, and we're going to add a small bit of the residual back into it. And I won't prove to you that this actually works. It depends on your choice of omega, the scalar value. But the point is that, even with this very simple scheme, you can take an arbitrary guess and converge to the true solution. It just does so very, very slowly. And there are much better methods than this. We'll talk about some of them later. But really, this is the basic essence of an iterative method. So the things that we'll talk about later have the same real core components. They just do more sophisticated things. Like Richardson iteration just takes the best notion of what it has for the direction to proceed, goes a little bit in that direction, and then starts all over again. Different methods will pick the directions that they improve the solution in a more principled way, and they can converge much more rapidly. Okay, so if you look back at Richardson iteration, it is the simplest method you can come up with, but it really has the same components that others do. And these are, I just want to highlight the major algorithms or operations going on here. The first and most important, most costly thing is sparse matrix vector multiplication. So by that I mean just taking a sparse matrix A, multiplying it by some vector x, and storing the result in another vector y. We have to do this, once each time in Richardson iteration. The other operation that we had to do was this scaled vector and add. So we take a vector, we add some multiple of another vector, and save that back in the same vector. So there's lots of different variants on this, but this particular one happens to have a name in this BLAST library. So BLAST is a collection of common linear algebra things that show up in lots of places. And the reason to put them in a library is that every vendor, so NVIDIA or Intel or AMD, has their own high-performance implementations of these. So if you use a BLAST kernel, or if you write your algorithms in terms of BLAST operations, like Saxby is the name of this one, then you'll get the best possible performance for a given platform. The last operation is the vector norm. So that shows up when we want to decide when we have reached, or when we have converged. So we take the norm of the residual, and we compare that to our tolerance. So this norm is just, taking the entries of the vector, squaring them, summing them together, and then taking the square root. So it's your standard 2-norm or Euclidean norm, and that is also a BLAST routine. So if you're thinking about, on a GPU, you might think about how to parallelize each of these. The first one is going to be the thing that we study in depth in the next lecture. Saxby is very straightforward to do. It's actually, often the first thing that we teach people to do on CUDA. It's very simple to parallelize. You just read in, the entries of the vectors, scale one of them, and then write it back out. The vector norm's a little more difficult just because you have to do a reduction. So if you're not already comfortable with that, we're not going to study it ourselves, but you might look at the CUDA SDK or just read some other resources to understand how one would, compute the sum of an array efficiently in parallel on GPU. Okay, so now we're going to look at different ways of representing sparse matrices. I apologize, I didn't know that Wenmei was going to present some of these slides last week, so he kind of stole my thunder. But I do have a bit more to add to that, so it's not completely redundant. The simplest way that you can store a sparse matrix is this so-called coordinate format, or often abbreviated COO. And in here we have at the left a dense representation of a matrix. It has, I guess, how many? 9 non-zero entries. And I've sort of circled some of them and shown where they appear in the coordinate representation. So at the left we have the dense representation. At the right we have the coordinate representation. And there are 3 different arrays in the coordinate representation. We have the row indices, the column indices, and then the non-zero values. So it's pretty straightforward to see what happens here. By convention, we sort of pick the first row and just start going left to right, second row, left to right, and so on. And I've shown where the entries appear. So the red entry, the first element of the matrix, has the coordinate 0, 0, and the non-zero value 1. Then we go to the green entry, 0, 1, and the value of 7. And so on. So it's very straightforward to see how this format works. It's sort of a very verbose format. Some of the formats we'll show later are more compact. But it's sort of an attractive thing to work with because you can manipulate this structure very easily. If I asked you how many non-zeros in the matrix, it's very simple. It's just the length of the array. If I said what's the maximum, value, you could very easily, just search, do a reduction over the values array. So it's very attractive to manipulate, and it's not a bad format to use in general. An improvement on this, which is called the compressed sparse row format, or CSR, looks very similar. So if you look at the difference between these two, the column indices and values array are actually exactly the same. All we've done is sort of optimize the row indices by doing a compression on it. So we've done sort of a run length compression on it, essentially. And usually this is a benefit, because if we have lots of non-zero entries in the same row, we don't need to represent, this sort of redundant information. We don't need to say 0, 0, and then 1, 1, and then a bunch of 2s. We can just say how many there are in each one. And the CSR is an attractive way of representing that. So in most cases of interest, the CSR is actually a more economical storage scheme than the coordinate. And it's really, we're not sacrificing anything. Another attractive property of this scheme is that if we want to get the entries of a particular row, so if we want to index into the third row of this matrix, we know exactly where we want to start. We want to look up in this row offsets array. We're going to go to the, look up the third entry, so 4, and that's going to tell us where the entries for the second row, or the third row begin. So we'll look up here, 4, come to this place, and we'll know that from 4 all the way up to here, so everything before 7 are the entries in the third row. So it's very attractive, and this is sort of probably the most popular format and most common because it gives us a very compact storage scheme, and it also lets us look up entries very quickly. So if we went back to this and we said, I want all the entries in the third row, you'd at least have to do, if we sorted it like we did here, you'd have to do a log. You'd have to do a sort of binary search to figure out where to go. That's not so bad, but if you're doing lots of these queries, then it's kind of undesirable. So CSR, a very popular format. It's the one underlying a lot of sparse libraries. LPAC is, it's named, we often abbreviate ELL. It's named LPAC because that's the numerical package that it introduced this. It was sort of the native format underlying that. It's not really too important. It's just sort of a historical note. With LPAC, it's sort of a mix between what we described before. The main thing in LPAC is that it sort of imposes regularity. Like in the previous ones we looked at, there are really no assumptions on the sparsity pattern of the matrix. We could store anything. Like you give me a completely random matrix. It's not too bad to store it in coordinate or CSR format. In LPAC, we're going to make one assumption, and we're trying to, in many cases, we can exploit this to positive effect. The assumption we're going to make is that there's some maximum number of non-zeros in any row, so in this case 3, and that most rows have about this number, or close to this, so maybe half or more. So in this case, we're going to say I have at most 3 non-zeros per row. I'm going to reserve that many slots for each row. And if I don't have that many non-zeros in each row, I'm going to put a value, just some padding in there. So I represented that with an asterisk. So that might be, a -1 or a 0 or something like that. Doesn't really matter. It just means that we're reserving that spot just to make the structure align. So here, by convention, I've taken, the 1 and 7 from the first row. I've just put them in the same order in the LPAC structure. And likewise with each other row. So if we had a row with 4 entries, so if I added, if it was not 5, 0, 3, 9, but that 0 was some non-zero value, then you can see that we would be forced to add another column to this structure and insert padding in most of these rows. Question?
I think there's a mistake in the third row.
Oh,
I'm just asking.
you're right. Okay.
I've never seen this format.
So this should be 2 and 3. I will fix that. Thank you. So anyway, this is a good format if the number of non-zeros in each row is about the same throughout the matrix and there are no exceptional ones. It becomes a very, very bad format if I had, suppose I had a 100 by 100 matrix and there was one row that was really long, but most of them only had a few entries. This would become a terrible way of storing this matrix. Another format is the diagonal format. So this is similar to the LPAC format, but it's even more strict in what it says, and as a consequence, it's even more compact. So if you look at before, we had two arrays. We had to store the indices, so the column indices, and also the non-zero values. In the diagonal format, we get rid of the column indices, and we're going to only store things according to their diagonal. So, the main diagonal of the matrix is this. We're going to say that this is also a diagonal, and so on. So these are the diagonals, and the reason to look at diagonals is that if we have a structured mesh, then and we look at local neighborhoods of vertices, then the non-zeros of that matrix will follow this pattern. So even though it's a highly specific format, it sort of nicely encodes the patterns that arise in lots of computations. If you've used the spdiags command in MATLAB, this is the sort of idea. It's giving you a way of representing, you might pass it an array like the right, and it will, convert that to whatever internal format it uses. But it's a nice way of representing these types of problems. You can see here, the main diagonal, we put it in the middle, and we've just listed out the entries 1, 2, 3, 4. This would be this diagonal, 5, 6. And the way you can kind of imagine this is just like in spdiags, there's sort of fictitious entries up here, above this. And likewise, there's this fictitious entry here. And this is where we put the padding. So this upper diagonal, we put the padding at the end. Lower diagonal, we put the padding at the beginning. It's a matter of convention. You could shift the entries up or down, doesn't really matter. But this is the way we chose to do it. And just like the LPAC format, the length of the array, so it's a 2D array, and the number of rows is just the number of rows of the matrix. The number of columns is equal to the number of diagonals. So if I give you, just like LPAC, if I give you a matrix where I just add, if we added a 1 up here, then we'd be forced to add another column, although we're only going to use one value in it. So in the same way that LPAC can become very inefficient if we have long rows, diagonal becomes very inefficient if we just have people, non-zeros in the wrong places. So you only want to apply it to the sort of class of matrices that it was intended. Hybrid, this is the last sparse format we'll talk about, so if you're tired of these diagrams, I assure you this is the last one. Hybrid is something we came up with. I don't claim it's a great innovation because other people have done similar things in the past. But the idea here is to separate the matrix. So you can separate it into an LPAC part, a coordinate part, and you basically encode the matrix, or you treat the matrix as though it's the sum of those two parts. So here, the attractive thing about hybrid, I guess before I show how it's actually decomposed, is that LPAC was very good if we assumed that the rows were all very similar. They all had the same number of non-zeros. Coordinate, on the other hand, didn't make any assumptions. So we can put anything we want into coordinate. It's fine. It's not the best way of storing it, but we're not going to pay a disastrous overhead. LPAC, on the other hand, would pay a disastrous amount of overhead if we want to do something irregular in it. So combining these together is attractive because coordinate is not our favorite format. It's a little verbose, but it can handle anything. LPAC is we'll see later, is a very efficient format, but it gets very inefficient if we try to store lots of non-zeros in each row. So just splitting the two, so I've just arbitrarily decided I'm going to take the first two non-zeros in each row, put it in the LPAC format. Anything I get left over, I'm going to put it in the coordinate format. And as we see here, because all the rows have 2 entries except for the third row, which has 3, this is a very good way of storing it. We have no waste in the LPAC part, we have no padding, and our coordinate part is very small. Now the reason to do this, like you may at this point say, that was great, Nathan, but we haven't really saved that much. I've really only saved one value or so, maybe a few values in this particular case. But the reason this works out in practice is that if I give you a mesh, like in particular an unstructured mesh, usually you can say there are about 10 or maybe 20 non-zeros in each row, and there may be a few guys that are exceptional. There may be one row that has 100, and if you look at the distribution, there might be these tails, but these tails really punish us in the LPAC case. obliged to store those weird rows in LPAC as it prescribes, even though they might only represent a small fraction of the matrix. So in practice, what happens is if we store a matrix in this hybrid format, we can usually store perhaps say 90 or 95% of the matrix in LPAC, a very small percentage in this coordinate, and get the best of both worlds. We can get very efficient for most of the matrix, a little verbose for part of it, but we haven't wasted a lot of space encoding padding. So are there any questions about that? Because that's a nice thing to observe. Okay.
For sparse matrices, is the distribution of these extra long rows, is that about the same distribution as you would have for columns?
In most cases, we'd be working with symmetric matrices, like especially if it's a elliptic problem or something like that. So yeah, and we don't actually have to worry about the distribution of number per column, but yeah, it would turn out to be the same in most cases. Okay, so there's, as I sort of hinted at before, there's a spectrum of regularity. We have completely unstructured things where we know nothing about the sparsity pattern and we really can't exploit anything about it. And on the other extreme, we have the diagonal sort of format with lots of regularity and a very compact storage scheme, and lots of things in between. So there's not a strict ordering here, really, but the things like coordinate are tailored for this case, diagonal are tailored for that case, and the others fit in somewhere in between. And this is only a sampling. Like, people come up with weird sparse matrix formats all the time with some marginal advantage on one particular architecture, and they come up with names, novel names for those. But really, these sort of capture the majority of the things that appear in most places. So here we'll look at some different matrices, particular matrices, and then look at how that impacts the storage we need for each of them. And the reason that we care about how large the storage is because to first order, that's how expensive the sparse matrix vector multiplication is going to be. At least, at the very least, when we do a sparse matrix vector multiplication, we have to read the matrix in one time. So that's going to be the main objective here, to minimize the size of the matrix structure. So here we have a structured mesh on a regular grid, and you can see that because each node is connected to its 4 neighbors, we get 4 bands plus the main diagonal. And this is pretty common. So if you have a 2D mesh, this is pretty common to see. We get a main diagonal here, we get a diagonal just below that you can't really see so well, and a diagonal just above, and then you get these bands here. So our initial intuition should say this is stored very efficiently in the diagonal format. What would it say about the other formats? And we'll look at that next. Okay. So I've illustrated diagonal wins. It's green. If we store floating point values, so 32-bit floats, then we get by with only a little over 4 bytes per entry. And that makes sense because we're just storing the value, nothing else. If we're doing double, it moves up to 8 just because we're dealing with 64-bit numbers, but still very good, pretty much optimal. If we look at coordinate, that's the worst case. And the reason it's the worst case is just because it pays a penalty for each non-zero entry in the matrix, and it doesn't exploit the structure at all. So it doesn't really know, the coordinate format doesn't really know that this is a highly structured matrix, and it's not doing anything to exploit it. CSR improves on coordinate because it's going to compress the row indices. Each row on average has about 5, so it's going to reduce 5 row entries down to just a single value, so it gets some savings there. LPAC also more efficient because it's highly suited. Like second to the diagonal format is LPAC because this matrix very much meets its expectation. The number of non-zero entries is at most 5, and almost all rows have that exact number. Only a few of them on the boundary of the mesh have fewer, and they might have anywhere from 2 to 4. Hybrid. So I haven't told you how we're going to split a matrix in the hybrid format. I'll do that later in the next lecture. But in this case, hybrid would exactly coincide with the LPAC structure because it's going to look at it and say, aha, I'm just going to store this whole thing in LPAC. I'm not going to store anything in the coordinate part because LPAC is perfectly suited for this kind of structure. So So here we have an unstructured mesh. So the thing I've plotted here, if it's not obvious, is just the connections between the different vertices of my mesh. If I reordered it, so I can, I'm free to choose the order, and in fact I'm free to choose the order in this case too, but it just makes most sense to go, row than column. But here I've just chosen a way of ordering the nodes, and this is the matrix you get when you connect them together. So what should our intuition tell us about this? It doesn't have any obvious diagonals in it anymore. So we should think that it's not going to be very efficiently stored in the diagonal format. Okay, well, what about the LPAC format? Well, if we look at our mesh here, the number of neighbors of a given vertex is about the same. Like, you might have only 3 here, but that's a pretty uncommon case, 3 here. But most of these guys have, 5, 6, or 7. And that's a physical sort of constraint. The average is going to be about 6, just due to the fact that this is a planar mesh. So if we look at the way that these are stored, again, coordinate's going to give us the same exact number, 12 bytes per element in float and 16 in double. CSR actually wins this contest because it, it improves upon the coordinate, and it doesn't really make too much assumption about the storage of the matrix. Diagonal is, of course, the worst. And you can see how disastrous it is. Like, if you can't, like, you may be attracted and say, I want to use diagonal by default because it's the fastest. It's actually a terrible idea, because when you get it wrong, it's a huge penalty. Like, here it's a factor of, 10 or more versus the others. In some cases, it can be so bad that you just can't store it. So diagonal is, in a sense, unsafe to use. You can't just convert to it and see what happens. You have to first know something about your matrix to use it. LPAC, it's actually pretty good for this case, because as we saw before, the number of non-zeros didn't vary so much. It's not quite as good as before because, anytime we have a row with 3 entries and we have to pad that out to like 7 or 8, I don't know, maybe 9 or 10 in some cases, we're going to be wasting a lot of space. Hybrid actually fits between these, so hybrid improves on LPAC because it's going to not have so much padding, and it's almost as good as CSR in this case. And in practice, this is probably the fastest thing to compute with. Now suppose I go to a random matrix. Here I've just chosen the entries of the matrix randomly, so I take a random number for I, a random number for j, and then just put a 1 in for the value. We get sort of a similar relationship here. It turns out that LPAC becomes worse than before because there's more variance on the number of non-zeros per row. But again, hybrid is pretty good. CSR wins the race, and coordinate, well, it's always 12 and 16, so it's not terrible. So here's an interesting case. Most of the things I've shown you before were modeling like a physical mesh. So there was some sort of structure, even if it wasn't, like a diagonal structure. There was some basic, physical interpretation of what was happening there. Power law matrices, and I won't, rigorously define what that means, but they appear in places where you see vast differences between one thing and another. So if you looked at, friends on Facebook, some people have, 10 million friends like Barack Obama. Most of us might only have 100 or so. So this is sort of a power law where somebody can have orders of magnitude more connections than others. And this is sort of a synthetic representation of what that might be. So these occur in lots of places, lots of networks, social networks in particular. And a question is, how do we store this, or what does it look like when we try to store it in different formats? Again, you should say, we know diagonal is going to lose because there aren't any diagonals in this matrix. I certainly can't see any. CSR wins, coordinates not so bad, and LPAC is really starting to lose. Like before, we saw cases where LPAC was bad but not so bad. Here it's really starting to lose because the first row of this matrix, which probably has the most non-zeros, it has many more non-zeros than the last row, which would have probably the fewest. So if you reserve this much space, if you treat the world like everyone's a Barack Obama, then you're going to waste lots of space when you get down to the less popular members of your social network here. hybrid does pretty well, even though we just blindly converted to it. It's doing pretty well in this case, not far behind coordinate. But this is a case really where these more general formats have become more attractive. One question, so we have seen a case where CSR wins. We've seen a case where diagonal wins. Is there ever a case where coordinate can win? In most cases it looks like it's strictly an improvement on the CSR is strictly an improvement on the coordinate format. So a question you can take home with you, and I can tell you the answer later if you want, is whether the coordinate format can actually ever win. So to summarize what we looked at today, we talked about iterative solvers, and we'll give you a little bit more information about this later, and I can give you some resources to continue learning about them. Iterative solvers, they're going to measure the accuracy through the residual, and they're going to converge. We're going to say they've converged when the residual gets small enough. And you may say, no, this is not a valid thing. I don't accept the fact that I'm going to take an answer. I'm going to stop my algorithm when I know there's still some error in it. But actually, in most cases, this is okay because there's only so much benefit to solving the linear system to a certain accuracy. Like if you have a mesh and you have a certain discretization of that mesh, then you've already introduced some error. And that amount of error is sort of the threshold at which it doesn't make sense to continue solving your linear system to finer and finer accuracy. So most people will solve their linear system to a point where the error left in the, noted by the residual is comparable to the error left in the physical discretization. So finer physical discretization, lower tolerance on the iterative solver. We looked at different sparse matrix formats. There are lots of different options. You have to sort of be aware of this, unfortunately, if you want the best performance. If you don't care, you can just convert to this hybrid, and we'll show later that that's actually a good thing to do. And the thing we'll look at most carefully in the next lecture is just sparse matrix vector multiplication, and we'll sort of look at how the different formats impact the performance that we get out of that. Okay, posted some references here. You can just Google these for the most part. I will point out that there's this book available from Yusuf Saad at I guess, Minnesota. And it's very nice because the complete textbook is available in PDF form. And yeah, he just recently posted the second edition. So, a year ago this book cost you $80 in the bookstore. Today it's free in PDF online. And it's an excellent resource, so I highly recommend it. Anyway, thank you for your time. Question?
In those examples, so you have this parameter you can choose in the hybrid method, right?
That's right. So
was that the best case value of the parameter?
so the splitting that we pick turns out to depend on the relative speed that you get. So you have a kernel, a spin-V kernel for the LPAC. You have one for the coordinate. And a simple model just says if LPAC is 3 times as fast as this, then we're going to continue adding columns into LPAC until the relative proportion of them drops below 1/3. So there's a little subtlety in that, but it's a very simple model that we just empirically chose a threshold point based on some synthetic matrices and said we're just going to keep adding to the LPAC until the number of non-zeros in the kth column would drop below a certain value.
So it wasn't necessarily the best value for storage.
That's correct. The numbers here were based on the performance, so we were sort of ignoring. But the one nice thing about even that simple threshold is that it guarantees that we will never exceed some constant factor worse than coordinate alone. So there's an upper bound on the storage size, and we could incorporate that into the thresholding if we wanted to also. So anyway, the nice thing about this is it's simple to just compute a histogram over the row lengths and then pick it from there. So, any other questions?
If I want to use a hybrid solver, should I decide how to?
No, in our library, which I'll talk about in a subsequent lecture, it's sort of done for you behind the scenes. You could, in principle, say that, but at the current time, we just do make that decision for you. An interesting topic is how to pick, like hybrid is a good general purpose format that we came up with and saw some benefit from. An interesting thing, and we'll talk more about this tomorrow, is how to pick the best format perhaps automatically, or at least exploiting even more structure than what I've talked about here. So, good question.
by rest format, they just mean how memory efficient it is, or also how your solvers work?
So the first component, if it's a reasonable memory cost, then we're going to be almost exclusively interested in the performance. So there's some relationship between those, because if it becomes very expensive to store it, it's unlikely that we're going to be able to compute with it efficiently. But within the formats that are somewhat efficient, so within maybe a factor of 2 or 3 with respect to the best, we would in most cases want the fastest one. So that's what we'll look at next time. And it's not always the case that the most compact one wins, because the way that the memory will be accessed and stuff like that also has an influence on the performance. So.
If the matrices or in top of being symmetric, if they have binary values, are you do you do some additional saving on the bottom, like the bottom term of the part?
So you're saying if we have a symmetric matrix, can we exploit that?
In the case of binary values, like
Okay.
you have 0, 1.
Right. So in this case, I've just talked about floating point, but even our library and plenty of other packages will allow you to use maybe a byte for each of those. Or if it was just a Boolean value, then you actually don't even need to store the value at all. You can just say, I'm going to store the ones, and I'm not going to store the zeros. So if you were just storing an adjacency graph, then you wouldn't need a values array. You'd just drop that from these representations. So.
When you look at the diagonal matrices, what's the difference between direct methods and iterative ones in terms of performance?
Oh, so that's a good question. Let's see. With the direct methods, they will probably find a reasonable ordering. So if we, this might take a while to get to, I guess it all depends on how effective this reordering process is. So I believe that they are quite efficient. So the size of these, it's unclear in general how large they become, but if it's a regular mesh like this, then I think that people have proven bounds like, n log n, or maybe there's a square in there. So they can be pretty competitive in that case. Of course, it's also favorable to iterative methods that we can exploit this structure. So they both benefit in some way. So it's really just a matter of what the constant factors are, I think. In the largest scale, the direct solvers will lose, because even though that we have a diagonal matrix, these things will become much, much larger. So if you have a constant size problem, or maybe 10,000, maybe 100,000, then you might consider direct methods. They might actually be the fastest. If you go beyond that, you'll probably run out of memory, even if it's a structured problem. So just depends on the application. So okay, well, I'll be around all this week, so if you have other questions, feel free to ask. Thank you.